Okay, so we are on to our week that's covering correlation and regression. I'm going to focus the most on correlations, and at the end, we'll talk a little bit about regression. So, in keeping with a quick review from Psych 230, I wanted to review some main concepts in correlation. So, we're going to be focused on the Pearson correlations. So, you might have learned about phi or Spearman or the point biserial correlation, but we're going to be focused on Pearson. And so with Pearson, you need two error variables. When we get that R value between -1 and 1, it's associated with our strength of the correlation. So that's how close is it to -1 or 1, ignoring the sign. The sign of the correlation, which allows us to more easily interpret the data. So a positive sign is a match, both increase, both decrease. A negative correlation is 1 increases and 1 decreases. We also need to talk about significance. So there's significance in terms of statistical significance. Was there enough power to show this is a statistically significant relationship? But on top of that, we need to think about practical significance. So in this world of big data, we're going to find there's a number of different spurious correlations. So this idea of a spurious correlation is a correlation where it's really not very meaningful, but because it was such a large sample size, or there's just some interesting reasons why these two things seem to be associated with each other. So a correlation is run when you're interested in associations or relationships between two variables. We'll also talk about the correlation matrix. Again, a correlation is always about two variables, but you can run a matrix which shows associations amongst a number of different variables, all appearing in pairs. We're also going to talk about the regression. A simple regression is when you have one predictor, that a predictor is analogous to your independent variable, and one criterion. Criterion is your outcome variable. It's analogous to a dependent variable. We typically use the terms independent and dependent when we're using an experimental or quasi-experimental design, where you have groupings for your independent variable. All right, so we're going to look at some real life examples I've pulled, and we'll have a quick discussion with the regression towards the end. Okay, so my first real life example, for all of these examples, I want you to consider is this good science communication. So remember, I talked about SciComm when I shared the Time article for personality. So this is from Pew Research. It is a reliable organization. They put out back in 2016 a whole set of data looking at the nation's per capita income, smartphone ownership, as well as internet access. You can feel free to explore this information, explore the data they've run, but this shows a real life correlation. So there is a correlation of 0.84 for the relationship between national per capita income and smart home ownership. In other words, the higher the national per capita income, the more people that own smartphones. And you can kind of see where each nation is throughout that. So again, I just screenshotted this from their actual article. So they had shared that correlation. This is also an example of a scatter plot. You're able to see for each country where they're at in terms of their per capita, which is the bottom, the x-axis, and percentage of smartphone ownership, which is the y-axis. All right, so example 2. It is coming from another article with the Time magazine. I should have put that link in there. There you go. It looks at understanding what people who are not nutritionists think is healthy food and people who are nutritionists think of healthy food. So Time actually did a survey with a bunch of nutritionists and non-nutritionists and asked them, do you consider this a healthy food or not? So they bunched everyday folk in one group, nutritionists in another group. And so those are your two variables. And then they group them together. So you can see that they've generated a percentage. So for each item, they looked at what percentage of regular people see as healthy food or not healthy food, what percentage think of it as not healthy food. The y-axis is the nutritionists. The x-axis is we'll refer to as commoners. So I just So that line right there is showing you where they both agree. If you have foods over here, this is the case where nutritionists would say about 15% of them say slim one fast drink is healthy, whereas commoners think, somewhere around 47% think it's healthy. And this article is really cool because it does give you the data from their survey. So if you were to go on the link, which I'll give you a quick little preview, and also I want to show you it's way more. I couldn't screenshot all their foods they did, but these are all the foods they did. So again, this is a scatter plot, and this is correlational data because you're looking at percentages and percentages. And so if it was a correlation of 1, you'd see everyone agrees what is healthy and what is not. But you do see, again, with the scatter plot, we do seem to have a positive correlation. So again, the article goes through and shows you the actual data and has a nice discussion. So if you are more interested, feel free to check that out a little bit more. So this was another example, again, of a positive correlation. Here is another example. This is my third example. Again, for each one of these, I'll have a basic homework question asking, do you think this was good science communication or not? So I do hope that you explore the data. This is one of my favorite websites, flowingdata.com. So this is a scatter plot. And again, it is interactive. So if you are to go onto the website, flowingdata.com, if you click on each one of these dots, it's going to tell you the occupation. So I had went ahead and clicked on the one for psychologists, and that's where I clicked on there. It also showed some of them that we might consider more of the outliers, or they just weren't quite in this general pattern. So we can kind of see through the scatter plot that you've got kind of a negative trend here. So a negative correlation, think about how you would interpret that. So the more money that's made, we tend to see a lower divorce rate. Of course, we've got some cases where they don't quite fit that. So one exception is clergy, and that kind of makes sense. Another one that's kind of out there is bartenders, which I guess could kind of make sense too. So he was able to look at how salary was related to divorce for these different occupations. He has way more data on this as well. In fact, he even has another set of data that shows if you're an economist, who are you likely to marry occupation-wise? If you're a psychologist, who are you likely to marry education-wise? If you're a professor, etc. So it was interesting and entertaining for me to go through that with my husband and chat. And so if I put myself as a psychologist, you're more likely to have a psychologist. If you put yourself as post-secondary, it's also post-secondary. My husband is a business analyst, and so he didn't quite make the most common. It was interesting, though. I can see how psychologists marry other psychologists. So I also think this brings up a great point of discussion as well with correlation. Correlation is not causation. You should have already had that drilled in your head from Psych 101. But also consider that third variable problem. So obviously, I'm not going to go around and deciding a future spouse or partner or deciding my outcome if I'm married based on one's salary and occupation. There's other factors out there. So there's probably third variables. It could be maybe hours worked. It could be the type of job you have. It could be when you got married during that time. If you had to go to school, for example, for the physicians and surgeons, maybe you had put off marriage. So again, there's a number of these different other factors. Correlations just tell us two things that are related. They're not able to tell us how are they related to other things and what is that complete story. So again, check that out. So again, this idea of sometimes correlations don't mean anything. There's also this fun website. Of course, I'm going to say it's fun being a psychologist and loving stats, where he goes through, Tyler goes through, so there's the website there, goes through and shows you all these crazy spurious correlations. So again, this goes to the point that statistical significance isn't always practical or makes sense. So these things are statistically related, but they don't make any sense. So I just pulled one example. People who drowned after falling out in a fishing boat, and marriage rates in Kentucky. So again, some humorous findings there with his work. So again, something else to be cautious of. The other thing I wanted to point out, if you're having trouble kind of understanding, we've talked about eta squared and r squared in the past. If you had, and now we're introducing r squared as the coefficient of determination. If you're having challenges understanding this, go to this website and it allows you to slide across. So I slid, the middle would be a 0 correlation. If you slid over here, it'd be a positive correlation. And then it's showing you the r squared. And literally r squared is 0.64 times 0.64. And that's showing you that shared variance right there. In terms of correlation, you can say percentage of shared variance. If you move it up and step it up and have a predictor criterion relationship, which is the regression, it is the percentage of variance in your outcome that is explained for or accounted for by your predictor. We've used that terminology before in explaining eta squared with ANOVA, but now we can turn it the same kind of idea with this new terminology. So now I'm going to briefly talk for the last couple minutes about running a correlation in Jamovi. I'm having us work with Big 5 data. This is a common data set. If you have Jamovi, you could have it. It's already in there. It is the Big 5. You already know about the Big 5. We did Big 5 with ANOVA. With this Big 5, though, the outcome variable isn't the total score for each one of them. It is averaging. So for each one of the items in these multi-item scales, you responded 1 to 5, and then they averaged it all out. So I'm going to go ahead and pull through some of that data with you. So I'm going to quickly show you the data here so you can see a little bit more of it. You can see that, again, these scores here are based on 1 to 5, the average across all those items. So that's how you kind of interpret that. 5 is on the high end of conscientiousness, 1 is on the low end of conscientiousness. I'm going to go ahead and move this back there, and then I've got some output. I've got the output on the PowerPoint slide, so I'm going to keep with this. So this, when we're going through and doing the Big 5, you're going to see the Jamovi output. I did go through and show you, it was normal data. This was great data to run a Pearson on. And then this is the correlation matrix. Again, a correlation matrix, you're going to see how extroversion is related to neuroticism, how openness is related to neuroticism, how agreeableness is related to neuroticism, how conscientiousness is related to neuroticism. This p-value, if it's p less than 0.05, it shows it's significant. And then this is the actual r value. And the sample size was large in this data set. 500 people participated in the survey. So I'm going to have you answer a couple questions about this correlation matrix with your homework as well. And you will have an annotated output for this as well that you can refer to. I'm now going to briefly talk about the regression. So the regression in Jamovi is based on a data set that you already have looked at, campus involvement. We looked at it at the very, very beginning of the year. And now I'm going to run a regression on it because this is all data. So I'm looking at social well-being scores, campus involvement scores, and GPA. All of that is data. And so I'm seeing, can I predict student involvement on campus from their GPA scores and their social well-being scores of self-report. So again, I have the output for you, but the first thing I have to do in this is make sure my data is normal. So this is showing you we've got normal data, no issues of skewness and kurtosis here. Again, these are social well-being and campus involvement is on a 1 to 5 scale. GPA was on a 1 to 4 scale. And then I need to identify relationships. So the next thing I would need to do is run a regression. I can see that my outcome, I'm interested in predicting campus involvement. That is my outcome. That is my criterion. And I can see they are both related. GPA and social well-being are both related. That is great. I need to have a relationship before I can, and I need to have a reason of having a predictor criterion to run the regression. If I had something like the Big 5, I wouldn't run a regression on that because one is not going to predict the other. I'm asking them all, they're all personality traits. It's not based on time or any other previous information, etc. So then I'm going to run the regression. So here's my regression output. In your regression output, you first see if the overall model is significant. So it does give you an F. ANOVA and regression are related. I'll just tell you that. So this shows us we have a significant model. This also shows us the R squared. 19.8% of the variance in campus involvement is based on GPA, and then these show you both of these are significant predictors. And that in a nutshell. And here's your regression model equation.